Hello, everyone. Welcome to a Wolfram Language Design Review for version 14.3 about mathematical computation. And excitingly enough, first item is non-commutative algebra, something that we've been meaning to develop for 30 years. And many packages have been developed for it, but now hopefully we're about to have a built-in system for it. So, should I start with the guide page?
Yeah.
Is there a better way to find these guide pages?
Yeah. Click on that other icon there, because that system dialog sucks.
This
That,
icon
yeah,
here.
yeah, that one. And then just start typing non. There you go. Oops.
And
There.
why is this word non-commutative there? I see.
Yeah, so this was actually sort of a question that came up about the names and how we treat it in the documentation.
What is star star?
That is camel case non-commutative multiply.
Been there for a long time. Yeah.
Yeah, I understand, but it's not in this list. How
It's
come?
there. It's at the bottom. Yeah, right at the bottom.
Oh, because you don't care about it or what?
Well, because you won't kind of keep it as part of the underlying things, but it's not a core new operation. I mean, it's a question of how you want to put it, where you want to put it. But
Well, I assume if you're typing in non-commutative stuff, that it's okay. Well, let's start seeing some real things.
sure.
Is this where I should be going?
Yeah.
Yes, it's a good place to start. Yes.
So that basically parameterizes the kinds of non-commutative algebras that can be handled.
What's the relationship between this and axiomatic theory?
I mean, there is a bunch of axioms for it.
No. I'm asking, what's the relationship between axiomatic theory, which is a well-defined thing that we've had for a long time? We're not just going to build another layer that is, what's the relationship between axiomatic theory and this?
Well, right, an algebra is a particular axiomatic theory.
Indeed.
Right?
Indeed. But we have algebras in axiomatic theory, right? Like we have, like if I say axiomatic theory of, I don't know, Boolean algebra, Boolean axioms, for example. Okay, what do I get? How do I get the thing that has all the operations and so on listed?
I think we need Jose to give us that level of detail.
Then that's maybe what we need to get. How do we get the thing that lists
Right. I mean, the thing is that basically the non-commutative algebras we have are basically free algebras. So they only have the axioms of a generic non-commutative algebra.
Okay.
Whereas, Boolean algebra, all these particular algebras that are in axiomatic theory have additional, right? They have the constraints that define that particular.
I know, but you have an identity operation and things like that in what you're defining here. See, the thing is, we have a representation. Oh, how do I get this? Maybe we do want to ask Jose if he can join us.
Yes, I'll get him.
Trying to remember how we do this.
Do we have algebra axioms there? I see group axioms and.
Well, let's find out. We do not. But what we have, and I'm very confused by this, is we have a thing that has very much like what you're doing here, where you specify, what.
Well, it's quite different though. So we don't give the axioms there. You just
I'm
specify
aware that
the
we
names
don't
of
give
the
axioms.
operations.
Yes, that's right, and we have a way of doing that here. Do you see what I'm saying?
Okay.
That's why I'm telling you. That's why I'm telling you. It's a very similar thing.
I think that there are presumably side relations somewhere. That's would be my guess, because that would fit. You
Let's
know, and
say
that's what we
something
do
like,
in Grosvenor basis too. You know, and it,
okay, see that? See that? Does that look a bit like this or not?
Yeah, it does.
bit.
A
Yes,
bit.
it does.
Right,
It's
right.
called,
And you,
it's the same thing. But that's okay. I mean, you know, these functions don't do the same, but they have some overlap. Make sense?
Yeah.
right. And I think, right, I think we're basically doing it in a compatible way, right? You know, right, there's a default multiplication and addition, but you can specify your own, right? You can specify F and G, you can specify plus and times, which is pretty silly for a non-commutative algebra, but you can if you really want to.
Yeah, right. But okay, but that's, I mean, we call it unity here, we call it identity here, we got to figure that out. Those kinds of things. Make sense?
Sure.
Okay. So
Well,
let's take,
well, I mean, that's because a right, a group has an identity, right?
Well, do
Well,
Boolean.
An algebra has one or more unities.
yeah, okay,
right.
so fine. So we're doing different names for different types of axiomatic systems.
Looks like it.
Right.
And
Okay.
isn't this just notation?
No, because you can feed it into the theorem prover. See, if I say
No. But it sounds to me like each name here is hardwired. It's like using one of those parametrizations.
these names, like addition, for example,
Was
is,
wired into the field axioms.
that is
Probably.
correct. Just like multiplication is wired in here. But what this is notation. You are correct. This is specifying the notation,
Yeah.
right? But then what we can do is if we say something like, you know, and again, this is where, let's say we say f of p and q equals f of q and p, and then we say something like axiomatic theory. I think we do it like this. And then we say something like, I think this is right. Not right. Oh, I know what it is. It's operators goes to. Let me look. Oh, it's in a list because that's a separate property. Okay, so this is now going to do that proof using f as the operator. That makes sense?
Mm-hmm.
Which is very similar to what you're doing here, right? Right?
Yes. Mm-hmm.
Okay, don't resist it because we're going to have to figure out how to make these things compatible. So there's no point in pretending this doesn't exist. Okay.
Right.
Please
Well, this is right. It's you know, what we have is actually computational.
I know. Which obviously this is in a different way computational, right? So some of the things we're doing here, we could equally well expect that find equational proof will work if we had the algebra axioms, which we obviously should have here. Am I making sense? Does that make sense?
Well, I wouldn't want to commit to that, given that I don't entirely understand what Waldmeister is capable of, right?
Okay, that's not relevant here. If you give these axioms, it will successfully, I'm sure, it will successfully be able to prove things. It won't be nearly as efficient as the
But I'm
algorithms you have
thinking
over
about
here, but we need
I'm
compatibility.
just thinking of the parametrization. Okay, so let's think about. It seemed to me that underlying. So how do you add another set of axioms? You add a bunch of side relations, probably, like what is an addition inverse type thing?
Well, let's look at the axioms for a field. I mean, we can look at the axioms. I mean, I don't know what kind of, you know, we've got axioms for a field here. I'm actually very confused by that tilde sign and what that means. But be that as it may.
Maybe that's
Oh,
equivalent or something.
Equivalence.
Yeah.
There we go. So I don't know how that all works, but my point is, it should be the case that.
But so how do you get, where is the one?
I think it's there. It's called multiplication identity, inverse, addition
Okay.
identity, multiplication identity.
Okay.
Okay.
Right. So,
and well, let me point out that axiomatic theory is experimental, so we could make the decision that it should be changed to conform with.
Possibly, it's been around a while.
Yeah.
So, but something like this, changing the form of these axioms is not that big a deal, I think.
Yeah.
Right.
Jose's here, by the way. Yeah.
Okay.
Yeah, hello.
Hi. Why don't we have an algebra axioms in axiomatic theory?
I don't remember. There were some limitations at the beginning in what we could express with equational logic, but then Jonathan extended to first order logic, and then we could express more things. But I don't remember why we did
Okay,
that.
all right, okay, fine. But now we're trying to, you understand, but we're talking about this in connection with this, okay?
Mhm.
Okay, all right. So now we have the notion of this algebra. Now, all we're doing here, if I'm understanding correctly, is we're declaring certain variables to be scalars or commutative variables and so on. Is that correct?
Yes. Mhm.
Okay. So what's that dot dot mean?
non-commutative multiply.
No. I mean the dot dot underneath the two here.
It's
Oh,
the
operator power.
operation
Operation
Yeah, I don't think it's a dot dot. I mean, I can't quite see it that magnification, but
Well, didn't you implement
well,
it is
star?
star.
It's star star.
yeah, it's probably, you're right. Yes, that's showing, you're right. It's star star, right? So that's the second power using non-commutative multiply as opposed.
I get it. So one question here. What would the natural notation for this be if it wasn't for, the fact that we've got star star? Would it be a circle times, or what would it be? Or would it be a dot? Or what would the natural thing be that you would use mathematically?
I think different such algebras use different notations.
Right. So some would use juxtaposition. Some would use probably a center dot.
Some just use nothing. A B.
Or
right, i.e. juxtaposition.
a cross with a ring,
that's
like
called
tensor multiply.
Yeah. Okay. So I mean, what we've got here is circle times. That's what I said. We've got center dot, and we've got nothing. Okay. So I'm wondering if we can have a nice ligature that this star star turns into. That's something a bit more elegant and a bit less,
That would be nice.
So let's design it. Yeah, let's design. It's easy enough to do. We have a million ligatures in the system, like arrow and things like this.
Right. I think. I mean, do we want this everywhere or just in like operation power?
No, everywhere. And then we want to be consistent with whatever operation power. Then we want to make a thing that is. I like your way of doing operation power in principle.
Mm-hmm. So I think we just need to decide on a glyph, and then I add the declaration of the ligature. I'll have to double check with John, but I think that's all I need to do.
Okay,
so
fine.
If we can decide which of those two glyphs you want, I can start experimenting.
Neither of those glyphs. We need to design a glyph.
Oh, you want a new glyph? Okay,
I think so. I mean, it might be in Unicode, but we need to just decide what it is we roughly want it to look like.
Okay.
And I don't think it should be a dot on its own. I think it has to be something where when you see it, you have a fighting chance of knowing that it's a star star is how you type it in.
Okay.
So, I mean, the kind of thing I would immediately imagine are something that you get, and we're going to need graphic design. So that's another who's project managing here? Oh, it's Natalia,
I am.
right?
Yes.
So maybe at some point in this meeting, if we have time in this meeting, we could do 5 minutes with Jeremy. Otherwise, we'll have to do that separately. But that's going to
Okay.
be a need there.
Yes.
Okay. All right. Let's actually dig into the real content here. Okay. So if I don't give an algebra here, if I just do this, then it will do the right thing. Yeah.
Yeah.
Now, just so I understand, if we wanted, oh boy, I typed star at the beginning of the line. Okay. If we wanted, is this a conceivable notation for non-commutative power? And do we care? An infix notation. Am I making sense?
Not really. Could conceive. Well, the problem
You don't
is,
think anybody will type it in?
yeah, well, right. I think for maybe that one specific case, but right, basically every different power would need to be handled separately.
I don't understand why every different power. What are you talking about?
What?
Right. So you use star there, but what if you used F or circle plus, right? If you want that to actually, right, you're juxtaposing two operators that require operand, and that I can't just.
Okay, so what you're saying is that in your model, that you have, I don't really want, I mean, okay, so you're saying if I say operation power, well, let's see what it looks like.
You have to go to source.
Okay, now what's the difference between that and nest fx3?
It's
Well, right, one is assuming is actual application, right?
the second one is a unary operator, and here we have binary operator. So it's f
So
of
well, then what is it? Is it a fold? What the heck
it's a
is
fold.
it?
It's a fold. It's a fold. Fold f table xk.
Okay.
Right, and obviously it doesn't auto expand because it's a symbolic representation, right? So you could put an n there, among other things.
I understand. I'm asking what the difference is between, these things are not equal, obviously, are not double
Right.
equals equal. But these
I
things
think you want
are.
three. Sorry, I think you want three X's, not three F's.
I have 3 x's here.
You have four X's.
Well,
That's the fourth power. Yeah.
yeah, no, 3.
Now
Like
it's
this.
third power. Mm-hmm.
Okay. Can I use operation power on something with something? I mean, does operation power ever evaluate?
Basically if you have if the operator is a numeric function, so has the numeric function attribute and the x is numeric and k is numeric.
Okay. I'm not sure that's the only case it should, maybe normal of it should do something. I don't know.
Well, that's not evaluation.
What's not evaluation?
Applying normal is.
No, I understand, but it might change it into a form like this, which could then evaluate. Possibly. I'm not sure. Okay. So, okay. I see. So now, presumably, I can say directly in non-commutative expand, commutative variables arrow C. Is that correct?
No.
Well, you should be able to. Obviously, you don't have to encrust things 17 layers to be able to make this work, right? Why
Yeah.
wouldn't this work?
So have like, yeah, exactly with association there. Yeah,
Yeah.
we could do that. Yeah.
Right. This is a cheap version, so you don't have to always define the algebra. Make
Right,
sense?
and we did something like this in commutator.
Okay.
Or well, not exactly like this, but so I guess can you use the short names in non-commutative expand?
Yes, I could
Yeah.
use the short names, but not the
Association.
association.
Okay.
What short names?
Oh, there are named algebras. So you
There's
can
a small collection of named algebras.
Okay, fine. Where are those?
There's a-
listed above at the top of the file
Yeah.
of
Which
the non-commutative
notes.
algebra. Yeah, here.
that last table.
Okay. Okay, so those are deeply reminiscent of axiomatic theory, right?
Yes.
Yes.
Those are much
absolutely.
closer.
And probably, I mean, like, is there a good reason? Maybe I'm very confused here, but if we were to say Boolean algebra here,
Well,
right?
it wouldn't be a true Boolean algebra.
No.
No, we want basically all of them are free algebras.
See that
So any algebra that's not free, it shouldn't be there. And Boolean algebra is pretty not quite
Yes.
not free.
Yes.
well, it's also not over a field, etc., etc. It's just
Yeah. Oh, it's also not the type of algebra. Yeah.
yeah,
Okay.
it's not a
It's
vector
not
space over a field.
Not an algebra at all.
Okay,
Right.
so hold on a
We'd-
second. So tell me what kind of an algebra non-commutative algebra deals with.
So it's a free algebra over a field. So it's a vector space with multiplication.
So it has
Okay,
a
'cause it'd be
bilinear.
nice to get a
The
different.
multiplication is a bilinear kind of operation. That's the main.
Yes, I understand. So let's talk about two things to cross. Okay, so we would love to not have something as heavyweight as non-commutative, possibly as
Right.
the prefix.
Yes.
But then we're caught in the pincer of what about star star, which for 35 years has been, has been represented as non-commutative.
Exactly.
Okay,
Exactly.
so we're caught in that little pincer, right? I don't think it's inescapable, but we need to think about it. And the question of escaping it depends a bit on how important it is. If we've got a really fantastic name to use instead of non-commutative, then we start to think about it. If we don't, then we shouldn't rock that boat.
Also, part of the discussion that Adam and Jose had, I was thinking about sort of modeling more kinds of non-commutative
Yes.
algebras.
So, for example,
this is slightly limited, in that if you have certain commutation relations, there can be sort of an optimized representation of that is more built in.
Sorry, say that again. What?
So when you commute, in that multiplication operator, some of them satisfy a nice relationship, like many common non-commutative algebras.
Clifford algebra, yeah.
Well,
Yeah.
so let's be concrete. I mean, in quantum mechanics, for example, or symplectic things, in quantum mechanics, there's commutators. In classical mechanics, there's Poisson brackets, right? And there's also Lie brackets that show up.
Right. Yes. So, right. The symplectic algebra is a particular class of Lie algebras. In quantum mechanics, you mostly deal with just purely Lie algebra, with general Lie algebras.
Right. But so now how does that relate to what we can deal with? Because, I mean, those things have a relation.
Exactly, which is why they don't fit into what we have done thus far.
Well, we have several application examples which actually show all of them in some, like the Weil algebra and the Clifford algebra, and it's cool.
Well, I understand, but those things are also segues.
Those are more
axiomatic
along the
theory.
way. The way we show them is like for Grobner basis, right? isn't that?
Right,
Yes,
right.
yes, yes.
You
Right.
have to you have to add relations manually.
Right. You add relations manually, a little bit like you guys do with the Waldmeister, you know, those axiom systems.
Yes. It's an exciting fact that our find equational proof is still state of the art in terms of theorem proving. Just saying. Even though we really haven't touched it in a couple of decades. You can see some nice examples in something I wrote recently. Okay. So you're saying generic non-commutative expand or non-commutative operations generically have no
Constraints.
yes.
Yeah. So
We should be able to add constraints, in which case we've got an axiomatic theory, the same structure as an axiomatic theory. So axiomatic theory right now is something which its default is to return just a set of axioms, which is presumably very similar to the second argument that you would give, or the relations that you would put into a non-commutative algebra specification, correct?
Well, in a sense, except you don't put them in.
Well, where are they? Where do they go?
They are a separate thing. You have to define the relation, compute the Grosvenor base, and reduce with respect to the Grosvenor base.
So that's silly. I mean, we shouldn't need to do that. We should be able to just give the relations. And why are we making people do all that stuff?
Basically
because of some efficiency concern.
Yeah, so it would be terribly inefficient to use this technology for.
Yes, I understand. But what we should be doing is, if you give something with a bunch of relations, there should be some way, if we're going to have something that's called non-commutative algebra, then let it grind. When you give non-commutative algebra, let it grind to cache those bases and so on. Does that make sense?
There are a few other things, like relations may have to involve variables, and you don't give.
Okay, so that's a scoping
in the
issue.
Algebra itself,
I understand.
You don't give non-commutative variables.
Right. We already crossed that bridge with axiomatic theory, so we've already addressed that issue there. So we should use that mechanism.
What does it do? There?
Well, I mean, we've got things like 0 tilde being. Let's come to that in a second, but let's just get the big picture first. Okay. The big picture is you've got certain algebra. So I'm a little bit confused by something. So up here, the free algebra, I understand. Okay. All of these other things, do they effectively have relations or what?
No, they are all free algebras with different names for operators. That's all. That's all the difference.
So when you say different names for operators, it's like, do they all use non-commutative multiply for multiplication, or do they use?
No, matrix algebra would use dot. Composition algebra will use composition, and tensor algebra will use tensor products, and that's the whole difference. And matrix algebra will have symbolic identity matrix for the identity, and zero matrix for.
Okay, so
or zero
just
algebra.
To be clear, then non-commutative multiply is a specific multiplication operator. So this thing, non-commutative algebra, doesn't really go with non-commutative multiply, because non-commutative multiply is just one of the multiplication operators that could be used in these algebras. Is that correct?
Yes. That's why it was at the bottom with sort of generic operations in non-commutative algebra on the guide page.
Right. Yeah. So that will justify having a prefix that isn't non-commutative for all these things like collect and so on, possibly, if we can come up with a better prefix. Do you see what I'm saying?
Yeah.
Yes. Just couldn't think about better prefix. So for the algebra, it would be free algebra would be better prefix for algebra, but
I understand,
but not for anything else.
I understand. So we need it, but it's already confusing that these things are called things like non-commutative collect. when they also apply to just things like, matrix products or something. See what I'm saying?
Yes.
Matrix products are fine.
No,
Yeah.
Roger, look, a matrix product has a dot in it. Okay?
Yeah.
Which
Right. So the fact
Yeah.
it's called non-commutative collect is silly, given that what it really could be called in that case might be something like matrix collect, except we want to genericize it.
Right.
although dot is non-commutative, right? So-
I understand.
Yes. But
The-
yes, I understand the concern. Right, right. I'm just not sure that there is a sort of a better name that isn't actually
Okay.
twice as long.
Okay.
Yeah, it
Let's
could be
not declare
algebra as
defeat.
prefix. So,
Yeah, I don't think that's great. I mean, algebra, I was thinking about that. I think that's not great because algebra generically means the algebra invented by, Vieta or somebody. That is the algebra we use with, with ordinary operations.
Yes,
Right.
right. It would have to be like NC algebra or
NC,
something.
exactly. But then NC is something that we know about. So
well, it's already a non-commutative sort of only short. So
Yes, exactly. Right. And it's
I mean, the other possibility would be something like generalized expand, but I'm not sure that helps anything.
yes.
An alternative approach might be something like, this isn't quite right, something like operator expand.
yeah,
Or
that,
I was thinking that or operation expand to go with operation power.
yes, I think that looks very reasonable actually. Yeah.
Operation power reminds me of sort of operation, jungle capture or something.
Yeah.
You know,
Yeah, I agree. I didn't like it for I didn't like it for
Operation
same.
Iraqi freedom.
yeah, something like
right.
that.
Although the thing there is an operation, not an operator.
I understand it's not an operator form in the sense it has subvalues. I mean, to me,
it's also not an operator in the sense that an operator is typically a unary thing, and this is a binary thing.
Yeah.
I have to say that I am sort of partial to generalized power. Or possibly something like function power, but generalized power. If I saw that, I would have some idea what the heck it might mean.
Yes, I can use Lou as a data point as another person who was very confused by the name Operation Power when I first discussed typesetting ideas with him. So,
Fine.
whereas generalized power might have been, may not have been completely clear, but at least it wouldn't have been confusing.
Right. Okay, so operator expand is not quite right, but let's take a look at some of these other things. What is it that we are? I mean, we're expanding for general operators, but the addition, is the addition always commutative?
Yeah.
Yes.
Yes, by definition of an algebra, right? The addition must always
Yes,
be.
it's a vector space.
Okay,
so
but
the addition is from the vector space. So
okay,
it's
but
commutative.
look, we could imagine, could we not? What do we have if you remove the commutativity of addition? What kind of an object do we have?
Okay. Right. So we could call it a ring, right? Ring expand.
No,
Not
no,
quite.
that's just going to
It's
go
not a rank
crazy.
either. I don't think there is a. I don't know the name for the structure that would have two operations that are both not non-commutative and there is the.
What's a magma? What that's
A magma is even less. Right?
Yeah.
What
That's more
even
like-
less what?
It's the operations of, I believe a magma is actually less than a group even.
Yeah,
Right.
okay. I think that's right. Okay, but so I mean, let's find out, does this thing have a name, in fact? Let's see.
And the
During
equational
addition-
proof does have various types of ring.
Say it again.
Find the equational proof has axiomatic theory has various types of rings.
Does it have this type of ring?
No, this is more than a ring. An algebra is a ring plus another operation.
Right, but the ring also has the commutative operation, commutative addition. So I'm not sure that there is a vector space with non-commutative addition on which.
Who said it's a vector space?
Well, the algebra is a vector space with multiplication. So what do you use instead of vector space to get an algebra with non-commutative addition?
No, but look, you are dealing with the fact that you've built a bunch of operations that deal with the case of commutative addition.
So in fact, non-commutative looks like a pretty popular.
Okay, so the claim of this uninformed LLM plus a bunch of stuff of ours here. Really? That's not what a quantum group is it? Anybody know? Well, we're definitely not going to brand it quantum expand, even though that would sound cool.
Right.
Okay, so there's a question here which we probably should get the answer to, and it might be that there's a good name there that would mean something. But basically, right now, what we're supporting with these operations is let me see if I understand the idea, right? If I were to use non-commutative expand on something with dots in it, is it just going to work or not?
No, you have to say that the multiplication.
So I don't think that's right.
We have array expand does that. Array expand would work just fine without anything extra.
Okay, so this thing here doesn't do anything.
Oh yeah, okay.
Doesn't do anything. But if I said array expand,
yes, then it should work.
Then it will work.
Yes.
Okay. Now, if I were to put in there a some other operator here, like the diamond operator or whatever else it is, right? Then, I mean, it's like distribute, which just eats whatever the outer operator is, whatever the inner operator is.
How does it know what's the outer and what's the inner operator?
Well, it looks at the structure of the tree.
Here the plus is the outer.
Fine. So it wouldn't work. So distribute as such wouldn't work.
Or I guess it would. It would distribute plus with respect to dot and it wouldn't care.
Yeah. Right. Okay. But look. For what you're doing, most of the things that you're working with, does plus stay plus typically?
Yes.
Yeah.
Well, in some sense of typically, yeah.
Well, what's a counterexample?
You can define both addition and multiplication.
I understand, but what's an actual counterexample?
With the name algebras, no. With the name algebras, it's always plus, yes.
Okay, what's an example not with the named algebras? What's an example that you can just come up with?
Well, I want to name addition F and multiplication
No,
G.
I understand that. I'm asking for a real example.
No, so in
there might be something.
Yes,
in
most mathematical notation, the addition is
what about in like
denoted
lattice
with
theory?
Denoted with plus. So
okay, what about lattice theory or sets or something where the addition is meet and join or intersection and union? Is that a case?
Then you're no longer vector space and field.
It's not a vector space. So vector space is So vector space addition is I've never seen anything other than plus used for.
Yes, I think so.
Right. You might use circle plus, right? If you have a natural tensor product structure, right?
Okay, but
like in quantum mechanics, right? Like if you have mixed states.
Yeah,
whatever,
okay,
but
that's a good example. Okay, but in a first approximation, if you type a plus sign, and I mean, in other words, we could just give in this generalized expand, we could in principle just give the name of the multiplication operator, and it would know what to do. Is that a fair statement?
The identity usually of, like a matrix identity is not one.
Okay, okay, fine. All right, so okay, so we might have a whole association worth of stuff. But maybe we
yes.
want an elided form where we just give, do this relative to dot. Because if I were to give an algebra specification which said dot is the multiplication here, would this
Then
be the same as
the,
array expand?
yes, I just tried that.
Okay. Okay.
So I just added non-commutative algebra of association, multiplication goes to dot. and
Yeah,
then
I get it. I get it. So does array expand have a similar scalar variables way of how does it deal with scalar variables?
badly.
Figures out.
You can, right, we had the idea of a scalar symbol, but we didn't pursue it for
Yes.
whatever reason. So you can declare something to be like an array of 0 rank, and then that'll
Okay, but
definitely
so
be a scalar.
okay, so we've got three different things here. We've got axiomatic theory, we've got non-commutative star, and we've got array expand and the various array operations, right?
Right.
They've obviously got to be compatible. So if we're going to support things like, scalar variables goes to whatever, we should support that for array expand as well.
Array expand has assumptions, so you can always say assumption that something is a real number.
Oh yeah.
Okay, but that's nice, but maybe we should also support this interoperability with scalar variables. Does that make sense?
Yes. So that was already in the, yeah.
Oh, and what about with non-commutative expand? What about using assumptions with non-commutative expand as well?
Well, it would doesn't need any other typical assumptions that we make. So typical assumption is something is an element of reals or something is greater than 7, and that won't affect non-commutative expand in any way.
Well, but it affects it that it's a scalar variable.
Right.
If it's greater than 7, it's a scalar variable.
Yeah, but why would you say that if all that it really cares is
No,
that
but
something
the
is
reason
a
you say
scalar
that is
variable?
because you know the notation for array expand and you want to use it here. That's the reason you would do it. Right? So you don't have to go look at documentation and learn another way of doing it. So, I mean, I think that these things should support all the different ways of specifying that stuff. But let's take a look at some of these functions because
Is right, just I mean, wouldn't, well, it wouldn't make sense here, but if you multiplied all of that by an E, wouldn't E element of reals or E element of complexes make sense as a declaration that that's a scalar variable because it's in the underlying field? Adam?
Yeah,
think so.
that would make sense. Although most of the other typical assumptions would not make sense there. So it would take assumptions, and then all it would do is assumptions is try to figure out that some things are scalars.
This is a huge mess here. That's an absurdly huge mess. What do we do to simplify this?
What's an absurdly huge mess?
Well, all these things where you have to declare all this stuff. What the hell is this?
Well, you
create
relations. It
yes,
doesn't.
I can see that, but why doesn't it know those already, given that those relations are just relations of matrix algebra?
No, but you want to put them in explicitly on commutative Grosvenor basis. So you would say non-commutative Grosvenor basis of what if you didn't construct the relations?
Well, I don't know why this is useful. I mean, this is useful because it's a way, the Grosvenor basis is a useful way of getting canonical forms. But so where are you making the canonical form? You see what I'm saying?
with
The last one.
not commutative polynomial radius is giving the canonical form in this case.
The very last.
The very last thing.
Okay, so the question is, how do we get to that without all the crud before it?
Right. So question is, should, let's say, non-commutative Gribner base know about array simplify? So it kind of uses the underlying. I mean, I guess that there might be a way to.
But in the
No.
end,
I
what
mean-
you're trying to do here, forget the Grosvenor basis, because that's just an intermediate thing that's convenient for implementation. Right? The Grosvenor basis itself is constructed from this set of relations, right?
Yes.
Where
and
do
you
the
have to-
relations come from?
Well, you just see you have free algebra. It doesn't recognize things like inverse or whatever.
I know,
So-
but so that maybe you don't want a free algebra. Just like axiomatic theory doesn't always assume that it's, something without any relations. Right? You've got an exceptionally messy way to specify, very low-level way to specify the relations here. I mean, they're almost
Well,
bizarre.
it's not just the relations you have to specify. You have to specify a certain ordering of the
No,
variables.
that's for the Grosvenor basis. That's to make the Grosvenor basis.
Yes.
To get the
but
canonical form, you do not need to specify that. That's an efficiency thing for the Grosvenor
you
basis.
do, because the canonical form depends on what order of variables you chose.
Okay, fine.
Yeah, it does.
Fine. But the same is true when you say, okay, so the point you're making is that whereas polynomial factorization over, the complexes, it doesn't matter what the order of variables is. You always get the same factored form. Is that a true statement?
Yes.
Yes,
But it's certainly not true that collect always gives the same form. That depends on the order of variables.
Right, or in other words, closer things to this, if you have some polynomial relations, like some equations are satisfied, and you want to eliminate some variables, or
Yes.
you have to say what order of variables is, so that you know what variables are supposed to be eliminated. So,
Right.
so
Okay.
that's
So what's got to happen here is the end result needs to be that we have a function that is some kind of non-commutative simplify. I mean, or maybe it's just simplify itself, but somehow you have to specify that variable ordering to know what you count as, quote, simpler or something. Does that make sense?
yes.
So, but we should be able to get rid of almost all of the crud here. We've got named concepts of matrix algebra. We've got, a bunch of things here. We should be able to just simplify this to the point where you are really just feeding in whatever you had at the beginning of this. I don't even know. I can't even tell what's what anymore. I don't even understand what's what. What's expr? Oh, okay. Expr is that original thing up there. So what I should be able to do is to basically say, let's see what we would like it to be able to say. We'd like it to be able to say non-commutative simplify.
I mean, in this case, array simplify should just return identity here.
I understand that.
Probably
I
does.
understand, but I'm trying to. Okay,
Right.
so let's try it.
But then you have to declare what A and B are.
Yeah,
Okay, so
you-
tell me what to do here.
Element AB matrices n, n.
Like that.
Or n, n, I think it has to be
Yeah,
same.
right.
Same,
Yeah,
same,
they
same
should be
n.
square if you're going to be using
Square, yeah.
inverse.
Didn't work.
Huh,
Didn't work. Okay.
that is surprising.
Do I have to? Is this not right?
I'm not surprised by it. I mean,
Is
this
this
is
not
the
right?
additional capability that we're getting now with a Grosvenor basis.
Okay, but then
is
this
just-
should be made to
Right.
work. Give it
Right.
using
So
the Grosvenor
it's
basis
certainly it's not going computed. I thought, since this is sort of known theorem, I thought it might have been there, but maybe
Okay,
it's
fine.
not there.
But so one of the things we'll do is to wire up array simplify so it
Sure.
uses this technology. Is that
Yeah.
correct?
Yeah.
Try changing the array simplify to full simplify.
Or array expand.
array expand?
Well, neither.
I'm not. I'm just guessing. Okay. No.
Positive neither would work.
No,
Yeah,
no,
it's just
Okay, fine.
I
So
thought
this
it
needs to
might
be
be
wired up.
hard-coded, but if it's not hard-coded, it won't work.
Okay,
Right.
this needs
Yes,
to be wired up.
right. I mean, I think, coming at this from a non-expert, but I think what the point Adam is making is right. There are an infinite number of relations and an infinite number of, so in order to make sort of any simplification, right, there are infinite number of relations depending on what you call your variables. So having, the algebra contain the relations is, not
Yeah.
really conceptually correct. Is that right, Adam?
Yeah, yeah.
I'm totally confused. So
Right. So it's not just right. Say we're doing this in matrix algebra. Well, inverse of A dot A equals the identity is one relation, and inverse of B dot B is a second relation, and for the infinite number of dots and those are all separate relations.
Right. And the inverse of A plus B, which we use here because we see it in the expression, and that has one more relation.
So you can't sort of pre-compute the needed relations because there are an infinite number of relations.
So, Stephen, we are obviously going to need a lot more time. So we have a different review coming up in 5 minutes.
Yep.
We could decide to continue this, or we could decide to go back. But maybe we should
hold on.
preemptively.
What is the second review?
It's geometry. It's discrete computation with Charles, etc. A lot
I
of
kind of
geometry.
think we should hit that because I don't want to block that. But this, look, I think you guys should have a bit of thinking about this because I mean, basically what, the pushback that I'm making here is, for goodness sake, first of all, we got to get compatibility between array star, axiomatic theory, non-commutative star, and so on, right?
I mean, we could also get bridges built. If you want to go from one to the other
I don't want a
perspective.
bridge. I think it's very straightforward. I think these are really close. I think we just have to interoperate these things. I just don't think it's very hard. I think we just need to, expect we're going to do it.
Just so effectively, the thing that you can do with those axioms is basically compute polynomial reduce and automatically compute a Grosvenor basis. It's basically what those guys do, right?
With
the theorem prover. The theorem prover effectively does polynomial reduce of a Grosvenor basis.
I suppose so. I mean, yes, insofar as they're both Knuth-Bendixing and so on.
Yeah,
but it's a bit fancier than that in what it actually does algorithmically.
No, I mean,
that's conceptually what's going on.
But I think, but essentially that's what is going on, right? Now, the question is what the use cases is for this other more algebra perspective. It's richer than that,
Well, it depends on what you're trying to do. I mean, if you're trying to do theorem proving for, look, it is probably the case. I haven't done it, but it's probably the case. If you give some algebra that shows up in quantum mechanics, like some algebra of, creation and annihilation operators in Fock space or some such other thing, okay? I believe it's the case that the theorem prover could eat it up.
Yeah.
Okay?
So I think that maybe we should articulate use cases. I think theorem proving is one. Is this a true identity? That's definitely one use case. I agree. I think another very important use case is simplification.
I agree.
And canonicalization and other things.
Which the theorem prover right now doesn't do at all.
Right.
And also the theorem prover is doing a different thing, which is it's doing the thing of producing a proof, which, this to its benefit doesn't do, because most of the time nobody cares about the proof.
Yes.
Most of the time, just the answer.
I mean, in a way, yes. In a way, we could equip it to do that. Like if you showed how the Grosvenor basis was computed, and
nobody cares. Don't worry about it.
Right.
It doesn't matter. I mean, it's doing a different thing. I mean, find equational proof is all about getting the proof structure. Okay. Now, people use find equational proof. I've certainly used find equational proof to determine if things are true.
Right.
Okay. Now, I don't think that's necessarily, I mean, arguably, we should have another function that determines that. And that function might be closer to, these non-commutative star functions. Okay, so I mean, there's a different bridge, right? Which is right now, find equational proof, gives a failure object if it isn't true, right? It assumes it's going to be true and expects to give you a proof, and gives a failure object if it isn't true.
I see. Okay, so it doesn't give a simplification or something like that.
Right, that's correct. It doesn't at all. Now, could we, rewire it so it does give a simplification? I think it's, as you point out, internally it has to be making something like a Grosvenor basis.
Yes.
And so, that's not been the way it's been thought through. Okay. But let's not cut that again. Something that's clearly useful is, given these axioms, given this statement, is the statement true? That's an extreme version of simplification.
Yeah. So you can see here below, by the next example, actually, this is a famous, it's usually called matrix inversion lemma. And yeah, this proves that basically.
Okay, fine. But then, then I would say that another way of proving that would be to say, find equational proof of this thing, comma, matrix algebra.
Right.
And then it would actually give a proof and blah, 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 which is a different thing. But then the other thing is, a function which we don't have right now called basically find if it's true.
Mm-hmm.
Now, maybe find if it's true shouldn't exist and it should just be simplify. And if it's, I mean, that's what we did for years, is we put, theorem proving into full simplify.
Yeah.
But it didn't really, it only was good, useful in the case where it's going to give true or false. In other cases, the equational logic theorem prover just flapped around and didn't do, if the answer was A plus B, it couldn't find that. Am I making sense?
Mm-hmm.
Yeah.
Now, arguably, there might be a way to get it to find that, but that's a different story. But let's just look back at this for a second, and then we should skip to the other meeting. Yeah, I mean, okay, I just want to make it clear that from my point of view, okay, non-commutative Grosvenor basis is entrails of the goat. I'm much more interested in the goat as a whole rather than how its entrails work.
Yeah. So I think right now with this stuff, the killer app, as far as I'm concerned, is matrix algebra by far.
Right.
And I think that maybe we need to tackle these other algebras too, where there are relations, the commutation relations exist. But I haven't really thought through workflows.
Well, those are like symplectic.
Yeah, or Clifford algebra and Weil algebra and all of those.
Well, so a question here would be.
And so even though we don't do it right now, I mean, we do it right now, but it's what you point out is it's sort of a more advanced interface. It's like non-commutative Grosvenor base where you have to put in those extra relations. And so we could set a goal of where we want to make this go.
Exactly.
We can't do it for this release,
no,
right?
I know that, but that's okay.
Yeah.
But let's figure out the goal. So, I mean, the first thing, which seems to me a very low-hanging piece of fruit, is wire up array star to use the new technology.
Okay.
Right.
Yeah.
Right. We definitely want to do that. So this is in fact, to me, was the killer reason to do this project.
I agree. So let's get that wired up. So it just magically will start doing more stuff.
Right.
And then the question of entrailing, so to speak, is, I mean, I would have thought, if we go up here, I mean, so this matrix algebra, that is array star, right?
Yeah.
That's going to be done by.
I mean, it's literally matrices. So it's a kind of
a part of array stars, because it's
part of array star, but an important part.
Okay. But now,
Those two, I think, are not super useful. The
Which
free
one?
algebra and composition algebra.
which one is the relevant one for quantum mechanics?
While, if at all, I mean, there's a while algebra, which is like anti-commutative, the commutator equal to something. So I think that's the one. It's an algebraic expression of the while algebra, basically. So you.
Okay, so one thing that, I did, God, 50 years ago now. God, that's shocking. Okay, is 48 years ago at least, is gamma matrix algebra.
Which one?
Okay, gamma matrix algebra. Direct gamma matrices, Clifford algebra.
That's a Clifford algebra.
Oh, Clifford.
So-
That's what I know.
Yeah.
Okay.
So
Right,
that's
okay.
on
Yes.
the
And right,
So-
and obviously matrix algebras are the canonical, Lie representations.
But
So-
for example, for gamma matrix algebra, okay, it's there's an anti-commutator, etc. But there are highly efficient algorithms, some developed by yours truly, for doing gamma matrix algebra. And I have no idea whether these methods with non-commutative Grosvenor bases, whether they would just effectively find or use those methods, or whether those methods are a dramatic kind of, special case simplification. I don't know. Those methods.
I don't think we know fully either, but I think Adam hinted that we could do it more efficiently if we knew
Well, so
that.
I'll give you a sketch of what happens there. What happens there, and it relates also to this whole geometric algebra story and so on. What happens there is that you can, oh God, it's been so long since I thought about this, but basically you know that this product of gamma matrices has to be in 4 dimensions. It's scalar vector, tensor, axial vector, pseudoscalar. Those are the 5 different cases, that the 5 sort of basic, what are they called? The 5 things, bivectors, I guess, that you can get. I'm sure that's the right term, but anyway, there's a limited set of possible things that can come out, and so you can basically match up terms, match up coefficients to make that work. Now I have no idea how general that is, and I don't. But that's a good example. Doing gamma matrix algebra, which back in the day, at least in the 1970s, was a quite computation intensive task.
How do you spell that? Sorry.
Gamma matrix.
Gamma. I see. Okay. So that's like a Dirac kind of thing, or Dirac matrix, or is it different from Dirac matrices?
It's direct matrices. I'm
got
gonna
it.
pull something up for you just so you know.
Got it. Yes, I know. Those I know. I know the Dirac matrix really well. So I mean, so I guess that relates to Clifford algebras and representation of Clifford algebras, etc. So I think we are good over there. So I have in mind actually that we should really have products rather than algebras. You want a Clifford product, you want maybe a Dirac product, something of that sort, which actually captures the essence of the algebra structure.
Right. Yes.
So I've made a list last night of those, like 5 or 6 of them, and that's what we plan for the next release. I know it would be nice to have it here, but it looks like it's not going to make it. But I think what we need is just a 6 or 7 of them. There's one very general one.
This never got this. This is from 1976, maybe. Oh, it says unfinished in 1979. So this has, I think, a bunch of gamma matrix things in it.
Oh, handwritten.
Well, I didn't finish it.
Oh, okay.
Here we go. This was a program for Maxima. These are the defining relations. Gamma mu, anti-commutative, gamma mu, gamma nu is this. And then you're computing traces of products of gamma matrices.
Yes.
And so then the drama comes, boy, that's where is it? It probably has oh yeah, this then there's a whole relationship to epsilon, to Levi-Civita tensors. But I'm trying to remember how. God, there are a bunch of these relations, blah, blah, blah. Somewhere here, I think there's a nice algorithm. Oh, here it comes, probably. The hell is that? Oh, it's just determinant. Yeah. So anyway, this is the type of thing one.
That looks like a Gram matrix there. That determinant.
Yeah, that's possible. Yes,
yeah.
that's possible. But this is the big. This is the thing. It's got epsilon tensors and it's got sums over pairs, and it is a place where, if I remember correctly. But this is all, this is the type of thing you need to do. And there isn't a very efficient algorithm. I wonder if it's in here. I can't remember. Yeah, here we go. This is it. Yes, those are the bases. Right. Any string can then be expanded in this form. And that's the right. Yeah, okay, so that's the main result. And I have no idea whether, I mean, in modern times, has that all been trivialized? Do you know? So the basic point is that you've got these products of gamma matrices, and you can always write them as some sum of terms relative to that basis. And nobody knows whether that's
So
kind of modular reduction.
I don't think this has been trivialized. There are fast algorithms, and I've seen Wolfram language packages to do these things. And also it has been generalized to other dimensions. This has a curious periodicity 8. And so you have to worry about 8 cases.
Huh. I remember I generalized this because I did a bunch of stuff, maybe after this was written, on dimensional regularization, for which you need to, and I thought it was only even in odd dimensions that it worked differently. But there's really a cycle of 8.
Yes, because it depends on relations to some groups and other Clifford algebras and the compositions, and yeah, there's a periodicity 8. Real cases, complex cases.
Okay, that was Fortran.
Hmm.
Okay, in any case, so, okay, well, half a century has passed. Maybe we should make this more streamlined now. But the basic point is, maybe we need to enumerate, which algebras do people actually care about? Because maybe it's a list of 8 of them or something, or 5 of them or something like that. And maybe they're big enough that they actually deserve whole functions. Like, I don't know.
I think when we focus on some of them, and we've implemented other such algebras inside of our solvers. So for instance, we make use of something called an OR algebra, which can specialize to the Weyl algebra when you use derivatives, and it specializes to a shift algebra when you use difference equations, or shifts.
Mm-hmm.
And we use that to do elimination of systems. That's how we deal with systems of differential equations or system of difference equations. It gives us a systematic way to do elimination in such kinds of problems. But we haven't exposed it. It's behind the scenes.
And it's more general than just Frobenius for matrices. It's for more differential and difference operators with a shift and a...
Right.
So we have all that internally, but in a way, that's the motivation for this as well. So.
All right. So look, we know where we're going here. Let's come back in a few days and do another review here. And I just got some extra time because some outside event got cancelled. So there'll be a little bit more time this week to do design reviews.
Okay.
So let's plan on that, and let's go to, well, some of us go to the other meeting on discrete geometry. But I'm really looking forward to seeing more of this. And I think, generalized power, I'm 90% certain is what we want to call that concept. But again, this is going to require more thought. And it may very well be that for this version, we'll end up with non-commutative Grosvenor basis as a key function, and we'll have a non-commutative family, expecting that in subsequent versions, we'll have a cleaner, simpler form.
Right. We actually planned simplify. It's just that we weren't able to do it. So it's it will require some thought and some non-trivial implementation. It's not something that can be just
For what?
immediately
To simplify itself.
Simplification itself, yeah. So using this stuff to simplify things automatically.
Yeah, I
That's
understand.
not
But
quite
array
trivial
simplify,
thing.
we do have to make work.
Yeah,
I mean,
yeah.
okay.
Well, hooking it up into array simplify is actually the sort of the easiest part of simplify, although it's not entirely easy because we have to sort of figure out what relations it should use.
Yeah, I got it.
From
I got it.
see, it's doable eventually, but yeah.
Well, how about that's the low hanging, that's the very juicy fruit. So let's see if we can get it picked. All right. Okay. To be continued. On we go to a different meeting. So people who are following this live stream, we are about to start another live stream on a different topic. Actually, oh, Nick comments. Any geometric algebra multivector can be turned into a matrix of complex or hyperbolic numbers with a linear map. If array star functions can handle hyperbolic fields, then geometric algebra should be trivial.
No.
They cannot handle hyperbolic fields.
No.
Okay. Well, sad.
Sure.
Okay. All right.
Okay.
See you guys.
Bye.
Bye.